Right, hello everybody, welcome to the first Bilbo Maths online tutorial. My name's Andy Parker. Today we're going to be looking at connected particles. First of all, I'm going to go through some stuff to do with the course. If you've got any questions at any point, please do email them to me. I get no feedback at all about what's going on. All I'm doing is staring at a screen. So my email address is at the bottom here, andy.parker@bilbro.ac.uk. So I've got my email open. If any emails pop up, I can obviously read them and I can get back to you. Okay, so just going to start off with a bit of information about what's going to go on in these tutorials. So they're going to be hopefully on a Tuesday and a Friday at 1:30 p.m. Provided nothing happens to me, we'll try and keep them regular at that time so that everybody knows what's going on. All the resources like PowerPoints, worksheets and things like that, you can get them from the course page, and that is here, parkermaths.com/year1 maths. We will also try and look at getting them on Moodle as well. I don't think they're there yet, but that will be there if you prefer to use Moodle. We'll let you know when that's all set up. And if you are a Bilbro College maths student, we will be expecting you to submit both the work from the lectures and also the homework that we sent that goes with it using Adobe Scan. So if you've not used Adobe Scan before, hopefully you've been shown in the last week of college. You can go to parkermaths.com/remote, and there are a couple of videos there which will show you how to get started with both the Outlook app and Adobe Scan. Okay, so the online lectures then. We've never done this before. Specifically me, I've done video tutorials before, but I've never live streamed anything. Which is well out of my comfort zone because I make loads of mistakes. So please do get in touch when you see me making mistakes. It's not if, it'll be when. There's about a 17-second delay on the video, so not too long. But I have got my emails open, so if I do make a mistake, hopefully we can correct it before too many people go wrong. Please ask questions as well. Send them through an email. Send me scans using Adobe Scan, or just send me quick questions. Just type them out. If I get inundated and I can't keep up, then I'll pass them on to all other members of staff who can hopefully offer some feedback as well. Okay, and last thing before we get started, if possible, try to use a computer because you can have the PowerPoint open at the same time. So when I ask you to have a go at some of the questions, you'll have all the questions in front of you. You can work through them at your own pace. And I've also put solutions on for as many as I can, or mark schemes, so you can check your answers to things when you're ready. And if you're stuck on one, you can obviously look at the solution first before you get in touch as we go along. Okay, so let's have a look at some connected particles then. Right, so this is an applied topic. We're in the mechanics section, and it's split into three broad areas. We've got pulleys, we've got something called force coupling, and we've got normal contact force. Now, you've probably met normal contact force before, but we do look at it in a bit more detail in this section and how two particles interact with each other. So, first of all, we're going to look at Newton's third law. So that says if object A exerts a force on object B, then object B exerts a force of equal magnitude but in the opposite direction on A. Okay, so we're going to look at that in terms of this little diagram that we've got down at the bottom here. Okay, so imagine this is, say, a little ball, and this could be a box that it's resting on, and then this is the floor down here. So object A is going to be the ball, and object B is going to be this box. So thinking about the forces acting on object A, we've got a weight force coming down, and because it's not just falling, we've got a normal contact force acting upwards. So the box is exerting a normal contact force onto the ball. But then we can look at it from the perspective of object B, the box. So there are lots of forces going on here that I want us to ignore for the moment. For example, the box has down here a weight, we could call this big mg, and we've also got a normal contact force from the floor, we'll call that RF. But the one I want to focus on for this is that there's not just the weight pushing down on the floor, there's also the ball pushing down on the box. So the ball exerts a contact force downwards onto the box. And the magnitude of this force here is the same as the force up here. going on here? Okay, so the first section we're going to look at in connected particles then will be on pulleys. Now, for the purposes of this, I'll try and tell you what might be worthwhile writing down. So I would suggest not making endless notes just as I'm talking along, because it might just go too fast, and you won't be able to write everything down, and you also won't be able to listen at the same time. Remember, you can just look at the PowerPoint in your own time anyway. So if there's any point you think that would be useful for my notes, just leave a bit of space, and you can obviously come back and look at it. So at the top here, we've got a diagram of a typical pulley system. So this bit here is a pulley, and we've got a string either side which loops over the top of the pulley, and we've got two masses attached either side. Just in case you're not familiar with what a pulley looks like in the real world, here's a diagram that you could think about. So we've got a rope going over a wheel which can move around, and then it's attached to something here, and if you pulled on the string, you would raise up the block. Sometimes, as well as pulleys, we're looking at pegs. There's no difference in terms of the calculations we're going to do. It's just a pulley is a wheel that will move around to allow the string to move, and a peg is just something that will be fixed and the string would slide over the top of it without it moving at all. So, in order to simplify the maths involved in the questions we're going to do, we have to make some assumptions to start off with, and I would recommend writing these down. In the exam, a typical question is state the assumptions you've used in this question. So we make two assumptions about the pulley. First of all, we say it's a smooth pulley, and that means there's no friction. And the purpose of doing that, if there's no friction in this string, remember it's just a single string, the tension holding this mass, pulling in this direction, will be the same as the tension on the other side. So these two values T here would be the same either side of the pulley, and that will only be true if it's a smooth pulley. The next one is kind of just stating the obvious really. It's a fixed pulley, which means it just doesn't move. It's not going to like move side to side or up and down. We also make some assumptions about the string. The first one is we say the string is light, and that just means the mass can be considered so small it doesn't affect the calculations. Now, part of the reason for that is if you imagine instead that this was a big heavy chain that there's attached to either side. As more of the chain came onto this side would get heavier and heavier, which means it would accelerate faster and faster on one side. But if the mass doesn't matter, that's not something that would happen. So a consequence of the string being light is that we have constant acceleration. And the second assumption we make is that the string is inextensible. So, with the string being inextensible, that just means that the distance between the two objects stays the same all the time. So if this drops down by say 10 centimeters, this one will move up by 10 centimeters, and they stay the same distance apart from each other. And well, sorry, that's not true. They don't stay the same distance apart, but the length of the string stays the same. But they do travel with the same velocity at all times, whilever they're attached to the pulley. Okay, I'm just going to give you 1 minute now if you want to write any of this down, because I don't want people to be struggling to write things, and then we'll move on to the next bit. Okay, in the next section, I've got some starter questions for you to have a go at. Now these are based on what you've done on the flipped learning. So I'm just going to back up a little bit and go to the course page and show you where you can find all these resources. Because if you haven't done the flipped learning, when I looked at the online homework book, it looked like about at least 90% of people had done them, probably closer to 95%. So this is not many people, but just in case you are one of those people, if you load up the course page that I mentioned earlier, you get to this page here. if you go down to weekly tasks, we are currently in week 24. So all the resources for this lecture are in here. But the Pulley's homework that we did was on week 19, and there was also a bit on week 20. Okay, week 19 would probably be enough for today though. So if you go into week 19, there's a video playlist, some lovely videos by Exam Solutions and Jack Brown that you can watch, and there are 3 questions on a worksheet to get you up to speed. If you haven't done that yet, I would recommend you pause it for now and you come back to this lecture when you've had a look at those, because otherwise it might just go a bit over your head. Okay, so in the next few questions, they're all on the PowerPoint. I'd like you to have a go at the questions, keeping these things in mind. It's really important that you're focusing on drawing proper diagrams with forces labelled on them, writing down force equations, and using clear mathematical notation. So I'm just going to skip through to show you the questions, and then you can obviously you can go through them at your own pace. Question 1 is this, and then there'll be a solution for it, which is on this page. Then there's question 2, which is one where it's on a table dangling over the edge. That was on the week 20 homework stuff. And then there's question 3, which is a typical exam style question with a couple of things going on there. Just give me a second, it turns out I've got low battery. Okay, so these questions will take you all the way to the end of slide 13. What I'll do, I'll give you about 15 minutes to have a go at these questions. Ideally, minimise this tutorial for 15 minutes. I'll put a timer on the board so you know when we'll be back, and have a go at them straight from the PowerPoint. If you do come across any questions as we're going along, please do email me. I'll either try and email you back, or I can just speak to you and tell you what I think you need to do on here. For those of you that maybe can't get the PowerPoint, what I'll do is I'll scroll through the questions gradually. You won't be able to maybe move on at your own pace, but you'll still at least be able to see them at some point. Okay, so have fun and have a go at these questions. Okay, if your only way of checking the solutions is on the video because you haven't got the PowerPoint open, you might want to just pause it on this slide. I'm going to move it on to the next question in a second, but you'll still then be able to check your answer if you are still working on question 1. Okay, here's the solution for question 2. Pause it if you need to so that you can keep it on the screen. Okay, we're going to move on now and have a look at extending what we've done so far. One thing to look at though before we do is noticing this last question, if you got onto it, we're starting to link in forces with Suvat equations, and that's going to come in more and more as we get onto some of the more demanding questions. So in these next few questions, just to save a little bit of space from time to time, we're just going to make the assumptions that we talked about earlier. We're going to assume that the string is always light and extensible, and we're going to assume that the pulley in the peg is always smooth and fixed. Okay, so here is the next question then. So in this one, it's a similar kind of situation to what we've seen before. Basically, all of the information is contained within this diagram on the right hand side here. We've got two particles of mass 1 kilogram and 3 kilogram. The 1 kilogram one starts on the ground, and obviously when we release this system from rest, the 3 kilogram one is heavier. That's going to fall down to the ground, and it's got 40 centimeters to fall. Now there's three parts to this question. The first two parts are relatively straightforward. The third one, part C, might introduce something that you might not have thought about before. So in terms of working out the magnitude of the acceleration, that's just going to be a simple force calculation. Part B, with the speed of the 1 kilogram particle hitting the ground, is going to be a bit of Suvat, and the third part we'll talk about when we get to. Now for parts A and B, I'm going to go through them, but if you want to simply try them for yourself because you think you know what you're doing, then that's absolutely fine. You're welcome to crack on with those ones. Okay, so first of all, finding the magnitude of the acceleration. Because we can't see the question, I'm just going to pop a diagram that I prepared earlier on here. In terms of writing all this down, I'm going to model a solution by writing it on here. But my writing using a graphics tablet is not the neatest. So at the end, I'll delete all the writing once I've done the example, and I'll leave it on the screen for anybody that wants to just see it, a neater version of it. So there's no need to really write anything down as we're going along. So to start off with, we're looking to find A. We also don't know T, but we're not required to find that. So all we're going to do is set up a pair of simultaneous equations with this. I'm going to show you a way you can solve them simultaneously on your calculator to save a little bit of time if you want to as well. So in terms of modelling this, notice how I've drawn two separate diagrams. You can draw everything on one pulley, but I personally think by having just separate diagrams with the particles on their own, it makes it easier to visualise what I need to write down for each calculation. So I'm going to start off with the 1 kilogram particle. Okay, whenever you write down a force equation and there's more than one particle involved, try and say which particle you're working with at any one time, and also try and say which direction you're resolving in. So because this particle is travelling upwards and accelerating upwards, it makes sense for me to write an R with an up arrow, which tells me I'm resolving vertically upwards is the positive direction. So going upwards, I've got T, so that's just going to go there. Downwards force is 1G, or just G. So that's going to be negative, so T minus G, and that's going to equal mass times acceleration. The mass is 1 kilogram, so this is just 1A, or A. I'm going to call that equation number 1. Okay, then for the 3 kilogram particle, I'm going to resolve downwards as positive. So in this case, I've got a 3G force going downwards, I've got a tension force going upwards, so that'll be minus T, and that's going to equal mass times acceleration, which is 3A. And I'm going to call that equation 2. Now the manual way to solve these equations is always the same for these kind of things. You do equation 1 plus equation 2. Because you'll be doing T plus minus T, which will cancel out. And I've got 3G plus minus G gives me 2G. And on the right hand side, 3A plus A gives me 4A. Which gives me A equals 1/2 G. Considering we're using G as 9.8 in this question, I don't need a calculator to tell me that that's 4.9. Okay, so that's part A done. An alternative way of solving these simultaneous equations. it's not necessarily quicker with these, but it's something that's worth being aware of. If I take these equations first of all, remember G is just a number. So I'm going to take equation 1 and I'm just going to rewrite it as T minus A. So move the A onto the other side, equals G. And then the other one, I'm going to do the same thing. I've got a minus T on the left hand side. Move the 3G over to the other side. I'm going to have minus 3A equals minus 3G. Now I could have moved them all over and not had the minuses there, but I was trying to keep the sides consistent. And then I can go into my graphical calculator. I can go into the simultaneous equation solver, and I can think of X as T and Y as B. So I can put one lot of T minus one lot of A equals G, which is 9.8. I've got minus 1 lots of T, minus 3 lots of A, and minus 3 times 9.8 on the other side. And if I press equals, I don't need it, but the value of T is 14.7 and the acceleration is 4.9. So one benefit of doing that is I don't have to then sub back in to find T if I need it. I can just look up here and get that. So 4.9 is the value of A. So here is a neater version of what we've just done. Also means hopefully if I make any mistakes I'll spot them. Okay, next up, part B then. Let's just go back and look at the question. Find the speed of the 1 kilogram particle when the 3 kilogram particle hits the ground. So something to consider here is because this string is inextensible, then that means that the speed that the particle's at will be the same. So the speed of the 1 kilogram particle is the same thing as working out the speed of the 3 kilogram particle. Okay, so think about it like this. This 1 kilogram particle is going to move upwards, and if the 3 kilogram particle hits the ground, it's going to have moved up 40 centimeters. And it starts at rest, and we've just calculated its acceleration is 4.9. So we can put all of those values into a Suvat equation and find out what is the velocity of this when it's moved up to 40 centimeters. So we'll start by writing down some values for Suvat, and we'll say that upwards is the positive direction. Okay, so we know that it's moving up 40 centimeters, but in SI units we write that as 0.4 meters. The initial velocity is 0 meters per second. The final velocity is what we're trying to find, and the acceleration, which we found earlier, is 4.9 meters per second squared. Time is not something we're interested in for this calculation, and so we need a Suvat equation that involves S, U, V and A. The one we need is V squared equals U squared plus 2AS. So popping our numbers in, we get V squared equals 0 squared plus 2 times 4.9 times 0.4. Okay, and because I worked it out earlier, I know that if you do that calculation and then square root it, you end up with 1.98 meters per second. Okay, so this is not only is it the speed of the 1 kilogram particle when the other one hits the floor, it's the speed of the 3 kilogram particle right at the instant before it hits the floor. Okay, so I'm just going to leave that on the screen for a few seconds in case anybody is writing it down. I don't want to just move on too quickly. And then we'll look at part C, which is the new part. Okay, let's move on and have a look at part C then. This is the part that requires a bit more thinking. So we're looking to find the maximum height above the ground reached by the 1 kilogram particle. So I've got a little bit of a diagram here which is going to illustrate the situation. We have the 1 kilogram particle is now 40 centimeters above the ground, but that's not actually the highest point that it's going to reach. So the 3 kilogram particle has hit the ground, and just before that this particle was accelerating upwards at 4.9 meters per second squared. But the reason this is being pulled upwards is because this one is moving downwards. As soon as this one hits the ground, it means there's no tension force anymore pulling up the 1 kilogram particle. So the only force that's acting on this particle now is G, because it's 1 kilogram, so 1G. Okay, there is no longer this tension force that was in here, that is now gone. However, because it has a velocity moving upwards, it's not just going to instantly stop and start dropping back down. It's going to move up a little bit more, because what's going to happen, this speed here, 1.9, is going to be reduced to 0. So it will move up a little bit more until its speed is 0 at some point here, and then it will fall back down. Okay, so what we need to do to find out the maximum height that it reaches is figure out this little extra bit that it's going to travel up. And all we need to do for that is a Suvat equation. We're going to do one on the 1 kilogram particle. Okay, but now that there's no tension in here, I'm just going to write that it's under free fall, which means the only force acting on it is its weight, or gravity. So, think about your Suvat values for this. Okay, we will take upwards as the positive direction again. S is the thing that we're trying to calculate. U is 1.98, which we calculated from the previous part. V at the very top is 0, because remember this speed is going to keep reducing until it gets to 0, and then it will be negative for the rest of it. So we want V is 0. The acceleration, because upwards is the positive direction, this will be minus 9.8. And time again we're not interested in. So same variables as last time means we need V squared equals U squared plus 2AS. So 0 squared equals 1.98 squared. Seeing as A this time is negative, I'll just put a minus sign in here to deal with that. 2 times 9.8 times S, which is the unknown. So we could move the 2 times 9.8 is 19.6. So we'll move this term over to the other side. That gives us 19.6S equals 1.98 squared, and then divide through, we get 1.98 squared over 19.6. If you do that calculation, you get 0.2. There's actually something I've missed out here that I need to go back and clarify. Sorry about this. When we were doing part B and we calculated 1.98, this was actually to 3 significant figures. And we need to make sure we're using the exact value here. So this was 1.97 something. I'd missed that because I didn't bother to type it into my calculator. I should have really put the accuracy here as well. So what that means is actually when you come to use this 1.98 here, it's not really 1.98. It's the exact value that you've got on your calculator. And if you either store that value or use your answer button on your calculator, when you do this calculation here, you should actually get precisely 0.2 when you do that bit. Okay. However, we've not quite finished yet, because this 0.2 meters here is how far upwards that particle will travel after the 3 kilogram particle has hit the ground. Okay, so from here we need to go up another 0.2 meters. We're already 0.4 up, so the max height is the 0.4 we were above originally plus 0.2 equals 0.6 meters. Okay, and that's the answer to this question. Okay, so I'll leave that one on the screen for a minute again. If anybody wants to copy it down, they can do. Okay, now that I've shown you that one, I'd like you to have a go at this example here, 1p. It's very similar to the one I've done in terms of what you're doing. A few things are in different places. When you've had a go at it, there's a solution on slide 19. I'll put that up later. I'll give you about 5 minutes. In fact, I'll give you a little bit longer because there's a few more marks than that. 3, 5, 6, 7, 8. I'll give you 10 minutes to have a go at this one. The solution's on the next page. And once you've done that, I may as well go over what we're going to do next anyway. So you can just crack on with it if that's what you're ready to do. So, after you've done the example that I've just had on the screen, this one, then I want you to move on to some questions. They're all in the PowerPoint. Question 4, the first one that comes up, will be on stuff you've already... This is similar to the example you're about to do. So if you found the example really easy, skip this one, go on to the next one. After that, there are, I think, 3 exam questions. 5 and 6, everybody should really be able to get those done. Question 7 is an additional one in case you get through those really quickly. Just something to note though, before you start those questions, they're all from older AQA specification exams. In that exam, G was always 9.8. In your specification, you're supposed to use a suitable degree of accuracy in your answer. So you should be giving your answer to 2 significant figures if you use 9.8. So it's just something to be aware of in the mark scheme. You should really give yours to 2 sig fig, but in the mark scheme it'll be 3 sig fig. So just be aware of it and don't think that you've done anything wrong if that's what you've done. Okay, so here is the question you're having a go at. Please feel free to email me if you've got any questions. Okay, with this question then, I'll just quickly go through the answer to all 4 parts of it, so that if you're struggling with any of it, you can get a little bit of help. Obviously, you can still email me questions. If you're not quite finished yet and you don't want me to spoil the excitement and surprise of finishing it for yourself, then feel free to pause it at this moment, and then you can check and see if it's helpful later on. So tension and the value of M. So tension is pretty straightforward. Here are our diagrams. In fact, for this one we don't even need simultaneous equations, because if you look at the forces on particle P, the only unknown is T, and so we can simply resolve vertically on particle P, and we get T is 4.851. Okay, following on from that, the next part is a little bit unusual. I'll display the solution and then I'll talk you through it. So we've got mg minus our answer from the previous part equals 0.9m. Here notice that m is the only thing we don't know, g is 9.8, m occurs twice. So all we've got to do is move both of the m terms onto the same side of the equation and factorise. That gives us g minus 0.98 in the bracket. If you want to, you could literally just work that out, 9.8 minus 0.98. But in the example I've divided through, put it on the bottom, simplify that, you get 0.55. Okay, part 3, calculate the speed when it strikes the surface. That was very similar to what we did before. It falls down by 0.36 meters, and so if we set the displacement to 0.36, starts at rest, acceleration, what we found earlier, you can use v squared equals u squared plus 2as, just like we did last time, and you get v equals 0.84. Part 4 is a bit that catches loads of people out, so don't feel bad if you got this wrong. You're not in a small minority or anything. Calculate the greatest height of P above the surface. Now, if you applied what we did last time, you've probably done the first bit. Oh God, something's missing from there. Just give me a second. Something has disappeared. I must have deleted it. I'm going to have to fill in somewhere. I'll have to work it out for myself as we go along here. Okay, well the answer's here. The answer is this last bit is a bit that catches people out. So I need to find that little extra bit that it travels upwards. I'm sorry this isn't in the PowerPoint. You'd be using v squared equals u squared plus 2as. So 0 squared equals 0.84 squared minus 2 times 9.8 times s. So move that. This is 19.6 again. So 19.6 s equals 0.84 squared. I'll just work out s on the calculator. Bear in mind this might not quite be right, because if this wasn't exactly 0.84, I'm going to get a rounding error. So I'm going to get 0.84 squared divided by 19.6, and that gives me 0.036. on there. So it travels up an extra 0.036. I think what I've done is in here, this part of the calculation is wrong. I'll correct it on the PowerPoint and upload it again later. What we would have here is, note that the part that people make the mistake with is how far above this starts here. Because they both started 0.36 meters above the ground, and P moves up another 0.36 here, we do want this 2 times 0.36. That calculation tells me how far it is before it moves that extra little bit up, which is 0.036. And if I add those together, hopefully I get this answer here, which is correct. I just obviously messed around with the solution and somehow deleted it. So sorry, that's a little bit messy here. So the answer is 0.756. This calculation was wrong. If you didn't get that answer, the most likely thing is you forgot that it moved up an extra 0.36 meters. Okay, so to finish off then, we're just going to be doing the questions that are in the PowerPoint, but I will still be here at any point, and I'll be able to answer questions. I've had a couple of emails of people with solutions that we want to check, so I'm going to go through and check those, but please do keep sending me questions, because otherwise I'll have nothing to do for the next half hour apart from sit and look at the screen, not knowing how things are going. Okay, I'll finish up in half an hour, but if you've gone by then, I'd just like to say thanks for joining us. Before I go, actually, I think it's probably a good idea to just talk about handing in the homework. This only applies, obviously, if you're at Belborough. If you look at the week 24 page, which is on the screen now, what you should notice is there's a checklist for submitting the work. Your teachers are going to be checking through all your work that you send through. It's quite a lot of work, so please do try and be considerate and take these things into account. You're going to be submitting it using Adobe Scan. There's a link here to the tutorial videos if you've not done it before. If we get a chance, we'll create a front sheet, and if you're lucky enough to have a printer, you can obviously print that off. Otherwise, for your front sheet, just write down what the task headings are here, and pop them in. We might actually also be adding a Dr. Frost in here, sneaky one at the end there, because this isn't actually that much work for the week, so please don't feel too angry at us for doing that. I'm sure you've got plenty of time anyway. So this work is due in on the 2nd of the 5th. That's not this Thursday, that's the Thursday after, because this Thursday you should have your homework from the last week of college to hand in. So in that, just submit everything that's on this page. So both of the lectures, some exam questions, some practice questions, and if you're lucky enough to get onto it, you can have a go at the whole of the IYGB paper this time round. Okay, so that's all the homeworks on week 24. Please do get in touch, like I say, if you've got any questions. Okay, so I'll just leave you now to have a go at a few of these questions. Right, for those of you that can't get the PowerPoint up or having difficulties with it, I'm just going to flick through all of the questions on the PowerPoint, so that if you want to skip through them at any point, you can obviously skip through the video and catch up whenever you need to. So I'll leave each one up for about 30 seconds, each slide, and then I'll skip to the next slide. Okay, I'm just going to go through the last part of question 4, so 4C. Calculate the greatest height reached by P. I'll just display the solution up here and talk through the different parts of it. So in this first section here, we're looking at the distance travelled by P before Q hits the ground. So just going back to the diagram here, initially Q is going to move downwards and P is going to move upwards, and we can calculate the acceleration at that point using a force equation because there'll be constant tension in the string either side of the pulley. Okay, and that's what you do in part A. You find that that tension is 4.9 and the acceleration, you could figure out, oh, the acceleration is 2.45, you're given that. Okay, so in the bit before it hits the ground, we know that these Suvat values are true. So we can find that the distance that particle Q falls and the distance that P goes up by to start with is this distance here, 0.11025 meters. Oop, sorry about this. So the next part of the calculation here deals with the part of the motion where Q has hit the ground, so it's there's no longer that tension force pulling P upwards. So the only force that's acting on P in this last part here is gravity pulling it downwards. So the acceleration is minus g downwards. What you could add in here is that the positive direction is taken as upwards. So it moves a little bit further upwards. That's what this question mark is here. It's travelling at 0.735 meters per second. We know that because in part B we found the speed when Q hit the ground, which is 0.735. So we know that's its initial speed. We know at the very top, the highest point it reaches, it's got a velocity of 0. And so we can use these values in a Suvat equation to get the distance travelled upwards here. So it looks actually like there might be a calculation missing here. So what we need, let me just check, that's definitely what we need to do. Okay, it's going to be similar to the one you did last time. This distance here, oh, let me think for a minute. Yeah, this is the distance travelled upwards by P, but this is also the distance it's travelled down, so I'll just put a little diagram on here. This is the start point here. There's some distance above the ground which we don't know. And we found that this distance is 0.11025, but that means this one will also be moving up by the same amount in that time. So like in the last example we did, we're going to need 2 times 0.1125 plus, and then this bit here is the extra little distance. Once it reaches there, that extra little distance that it travels up, that's going to be 0.0275. So I'll just do the calculation for that. And I believe that gives us, oh hang on, I've typed that in wrong. .248 meters.